Today I want to talk a little bit about some of the works we've been doing in large-scale and multi-device visual SLAM. Before I do that, just as a bit of motivation, maybe also shared pain with some of the people in the audience. Why do we do still research on visual SLAM, right? So if I pitched projects about visual SLAM to students, or you visit computer vision conference, you might get the impression that visual SLAM, all the benchmarks are solved, and the really only thing to do is Gaussian splatting SLAM or something like that. That is where the frontier is. And of course, to a certain extent, that is part of the success that visual SLAM research had in the last 10 years. So now we actually have devices, you can just get them and basically tape them to your robot, and you have very good local visual odometry that will just give you your state estimation, at least in a local time frame and local horizon. And we've seen works really using these. Now, I still think there's actually super interesting problems that we can explore. And just to show a couple of them, one of these is, of course, large scale. So while you might locally have a really good visual odometry, having this consistent over a really large environment actually is still kind of something that we don't have fully solved. And also, one of the interesting aspects of this is to get this computationally within a certain limit. And the other thing that I mostly want to talk about today is to extend this to multi-agents. So really having different kinds of agents in an environment spatially aligned. And the last thing I want to put a little bit of attention on is long-term. So in the end, I think we imagine robots operating for hours or even days, while most of the data sets that we have actually stop at like 10 or 20 minutes of recordings. Of course, this is limited by the kind of battery power we have for our robots today, but that also means this kind of problem of long term is even a bit unknown, and we don't even have data to really explore this. Okay, but to motivate first the problem of multi-agent SLAM. This is a video from a work that we've been doing for ICRA last year, and this is the view from a HoloLens. And we render the map of a robot that is walking around in the environment. And now the person wearing the HoloLens actually walks behind the curtain, but can still see through the curtain because we render this robot map spatially aligned correctly. And we can even see this little dog. So the person still actually has an idea where the robot is walking around in this environment. And of course, what we imagine this to be useful for is, let's say you have a construction site, you have 10 robots running around, you very quickly get spatial awareness of where they are, what they are doing, and how it's looking exactly in their local vicinity. So this is pretty cool, but what you don't see, of course, in this video is this is stable for about 3 minutes until actually the SLAM problem becomes so complex that your next update of your pose is taking 2 minutes. So you actually have this 2-minute drift in between what the mapping server has kind of optimized spatially together and what your current device sees. And very quickly, you don't have this overlay anymore because you have maybe 40 centimeters of drift or something like that, which a person really sees. So that problem behind that is, of course, the different viewpoint of these different agents. So you have the robot, and you have at a kind of ground height, and you have a person wearing a headset. And even though these two viewpoints are just a meter in height apart, the features that we have in the images to localize them with each other are actually very different. And most of them are actually very far away and concentrated at the center, so that doesn't really help us to register them correctly. Now, what we did, and this we just recently presented last week, was we get a lot of recordings. And this is our student Josh doing most of this work in recordings. We first go in with a ground truth device, then we went to the same space with our robot. And this actually has audio. Then we go into the same space with HoloLens, and we also go into the same space with an iPad. So we have all of these different devices recording the same environment, and we have a ground truth scan of the environment. And with this, we actually get what we call CroCoDL, which is the short for cross-device localization data set with 10 different locations. And these 3 devices that we've seen, some of them we even have recorded drones. And the important thing is we get actually ground truth accuracy in the poses of all of these different devices. We get this just as a teaser because the workshop is called Unifying. We also tried to get an overview of, isn't this kind of data already available? So if you want to have an overview over more recent data sets, I recommend to check this paper. And then what we get basically is exactly this. So we have these different devices, and we see here, for example, the viewpoint difference between the spot and the HoloLens in the ground truth trajectories here. And we get this for very large scale environments. So in this kind of ground truthing, we're not limited by line of sight to a total station or something like that. And of course, we also can't wear a LiDAR on top of our heads. So this is kind of the trade-off zone that we're in here. But we get up to 10 centimeters in pose accuracy. And how we evaluate then whether this is all working correctly is we can render our ground truth scans of the environments into the camera viewpoints that our ground truth pipeline estimates. And if this all aligns well, then we have an understanding of how good we are here. And we see this kind of actually very challenging visual environments. We see these kind of changes here. So this is a drone viewpoint, and we see the previous scan that we did was actually at a different point in time where different construction was going on in this large industrial hall. And we see exactly these viewpoint differences. So here we have a HoloLens view on the left in this greenhouse or the robot view on the right, and we actually get good ground truth for all of these different points of view. So what we get out of this, and this I think is something that really excites me, is we get actually confusion matrices between different devices. So we see on the top here the different devices that we use for mapping. So let's say you get a couple of different sessions from Spot to create a map of the environment. We all know how to do that. Now we get an image from the same or a different device, and you try to localize it. And on the diagonal, of course, we see what most prior research has focused on and what we have a lot of data sets on. And so we see that works really well. But as soon as we leave this diagonal, we see that there's actually a problem with cross-device localization. And it's not necessarily symmetric, but it has kind of specific characteristics. Now, this is actually for a very kind of decent pipeline, net-blood descriptor, superpoint features, light blue matching. So something that is even much better than most of the real-time SLAM frameworks that we have. But the question was also a bit, is this just a problem of image descriptor, or is it really a problem of matching? So what we can, of course, do is replace NetBlood as our retrieval method with a ground truth oracle. So it just gives you the image that already has the best overlap. And we see that even in registration, there's still a problem that we can't really register images of different devices that well to each other compared to the diagonal here. I'm sorry, somehow the microphone is super loud from the room. Maybe you can disable that in the meantime. So I just want to pitch one other thing. And of course, we've already heard there are these new cool models like Master, which give us really nice reconstruction, camera estimation, but also relative pose between two different images. And they do this based on large scale priors about the geometry that we expect in a scene. And we've seen already some experiments how we can apply this in SLAM, for example, with Master SLAM here, mostly in the case of monocular. Now, I think this is actually super cool to also look at a very different problem, which is these problems of scale, long-term and large-scale devices, environments. So we call this to go, and we have a preprint about this where we look at this in detail. We actually revive a very old idea. If you look at the regular visual SLAM problem, you go explore an environment and you find landmarks that you can triangulate from multiple views, and then you can optimize all of that together through bundle adjustment. Now, this idea of post-SLAM was always that we can go through an environment and we don't actually look at the landmarks, but we can directly construct loop closure edges between different keyframes in our view. And this, of course, means we just have to do post-graph optimization, but we somehow need to get these edge constraints directly between different poses. And so what we, of course, can do now with models like Master is we can estimate such loop closure edges in absolute scale from two views only. And this is very exciting to me because it means we can do much more sparse and scalable optimization in Visual SLAM. So we also look at the alternative, which is you can, of course, construct scale-free edges with any kind of matcher that we already have. And we look at a bunch of different alternatives, but the interesting thing to me was we could record really an hour-long trajectory through a building, walking up and down all the time with Spot, and we would get a really consistent map, much better than the odometer we would put in. And while most of the SLAM frameworks we tried would actually diverge. Now you might ask, don't we actually need a map for navigation? But I think, also the talk before already pointed a bit towards that. We now look much more at sparse and scalable representations such as scene graphs, which don't necessarily include a complete metric reconstruction of the environment, but still allow us to do super high performance navigation tasks, which don't even need any of that information. And just to also mention it, we have another work which shows the same for exploration. So instead of using the geometry to find frontiers in your environment, you can actually find them from images much better, and also use all the visual information to score their visual gain. And then you don't need anything about the environment instead of maybe the trajectory that you've already visited. So if we go back to our frontiers, I think these are the kind of things that I'm very interested. Of course, I want to also mention monocular is actually a really interesting topic in Visual SLAM. And I think the more you see computer vision researchers talk about learning from videos, I think the more we need monocular SLAM to make it easier to process these videos. And I'm pretty sure there's also more other things that are exciting mentioning today in the workshop that I've not even listed here. So where's the CroCoDL going now? I just want to mention we will have a workshop and challenge at ICCV coming up. At IROS, we will actually look at a challenge on active localization. And we then also extending this to multi-agent SLAM and figuring out what happens if you actually have multiple trajectories from different agents. With this, I want to close. And I don't exactly know when I started, so maybe there's time for a question. Otherwise, I will take questions on the chat. Thank you.
Thanks, Hermann. Questions if someone has one? Any questions from the room? Okay, you have one there?
Yeah, so I probably have like a more of a philosophical question. So I guess, when you talk about visual SLAM or map representations, right? People talk about them in like implicit sense or explicit sense or like semantic, geometric, different axes, right? So how would I'd say, in your, I guess, do you think people should start building more unified models, which can do all of these things together? And if they do, how should the benchmark for this look like? Like, how do you measure progress? Like, do you guys still use the, the existing benchmark suite, just benchmark on all the tasks together? Or no, you really have to come up with more creative ways of doing this?
That's actually a super interesting question. I think you can actually still separate the tasks quite well from each other, right? I think if we actually make progress by doing this in a multitask unified framework, then what we should see are kind of improvements compared from separating these. But it doesn't mean that we can't separate the evaluation, right? We can still evaluate localization and maybe navigation or object retrieval. And ideally, a unified model should be able to solve all of these better than methods that can do this separately.
And just quickly to add on to that. So whenever we talk about SLAM, right, it's mostly that you already have a capture and you're trying to reconstruct it in some sense. But then how does embodiment come into this, right? For example, when you have active perception or when you have action entangled, then the game becomes completely different, right? And I feel like in the current space, as researchers, we only think about reconstructing existing captures, but then how can we actually use this for more embodiment, right? Like, have you guys thought about this?
Yes, this is okay. So you're talking about the problem of active perception. This is
I guess
something...
in general action essentially. So how would you intertwine action with existing reconstructions or data you captured?
I think the best way that we have right now is to use the same environment, and then you have multiple versions of active agents, and you directly have to compare them at least in the same environment. Doing this in different environments with different methods is very hard to compare. And doing this on a data set, of course, doesn't make sense if it really should be an active agent. So yeah, I think there we get actually close to the limits of what we can evaluate. The active challenge that we do is actively localizing in the given reconstruction. This, of course, you can measure, but yeah, you're right. This doesn't really capture the full image of doing active SLAM with multiple agents, which is fully dynamic.
Yeah. So but yeah, anyways, very cool work. Thank you so much.
Thanks, Hermann.